So in our introduction to counters, we observed that the counters belong to a group of logic circuits that are referred to as state machines. And now we look at the two types of state machines that you might meet in sequential circuits. And one of them is Mealy state machine, and the other one is called Moore state machine. The major difference between the two is that Mealy state machine has external outputs which are a function of current state and some external inputs. So we normally express such Mealy state machine as being equivalent to y, which is a function of some internal input and the current state of the machine, which may be represented by the number of flip-flops present. And for our purposes, we may say that it has two flip-flops. So what we are observing is that we have an external output, which is a function of external input and the current state of the machine. And some of the counters that we have developed have shown such characteristic, and therefore it may be classified as a Mealy state machine. So one precaution that we should employ when we are designing or operating a Mealy state machine is that we must ensure that the external inputs, in our case we have used example of x, does not change at the same time as our clock pulses. If they change at the same time as the clock pulses, then our Mealy state machine will not function correctly. Our second type of state machine is Moore machine, and we say that in this second type, the external outputs, maybe y, is only a function of the present states only, which we may express as the states of the flip-flops in our state machine. So what we notice here is that it is not dependent on any external inputs. Doesn't depend on any external inputs. An example that we did earlier, this example here, is an example of Mealy state machine, because the Mealy state machine, the output is dependent on external input and the present states of the state machine. For example, this state diagram describes a sequential process that may be considered to be a Mealy state machine because we have an output y that we can describe as a function of the external input x, the present states of the state machine, which may be described by QA and QB. We have observed that in any synchronous sequential system, it is desirable that all flip-flops be clocked at the same time. We have had this kind of arrangement where we have one flip-flop and another flip-flop, and we have desired that they are receiving the same clock at the same time. But you observe that there are in some circuits that have large number of flip-flops, sometimes it's not possible to achieve this same clocking due to some unequal delay in the clock transmission path. For instance, we have a longer path that is being followed by our clock pulse. So the distance between the clock and our first flip-flop is definitely not the same as that from the clock to the third flip-flop. And therefore we are saying that this signal may arrive with some very small delay, and this may cause the two flip-flops being unequally clocked. So we observe that the transmission path is clearly dependent on the path length. Sometimes you might experience some capacitive loading along the path of the transmission, and sometimes the path may be of different types as you transmit between the source of the clock to the destination of your flip-flops, and such time differences that may arise between the clocking of two flip-flops is called the clock skew. Our objective in sequential circuit design is to keep this clock skew or this difference at the minimum level. If it reaches or goes beyond some threshold, then our synchronous sequential system may not perform as expected. So the key takeaway here is that what is the clock skew and what is the objective of this clock skew. So what we have encountered so far are what is called synchronous counters or state machines, and we have observed that the flip-flops are fed by the same clock pulse. However, we meet some other counters that are referred to as non-synchronous, in which case the flip-flops are not fed by the same clock pulse. Sometimes we say that the output of one flip-flop, maybe QA, becomes the clock pulse of the next flip-flop, say flip-flop B, which may be a D flip-flop. So we normally arrange them in this form. The output of QA becomes the clock of the next flip-flop B, and therefore we clearly see that while this one may have received a clock individually and the input D, this input DB will not be transmitted when we set this clock pulse, but rather there will be a delay until the output of QA is fed into QB. So this kind of sequential system is referred to as a synchronous state machine or sequential process. So we also talk about synchronous counters, which are binary, versus those which are not binary. Binary counters are the one that count, say, from state S0 equivalent to 000 to state S7, which reads 111 without skipping any of the states. So it will run from S0, go to S1, S2, all the way to S7, and sometimes back to S1, or going back to the S0. So if you are told to design such a circuit, you just need to follow the procedure that we have followed, and you would observe that the design process is quite straightforward. On the other hand, you may meet other non-binary counters that do not follow the numerical order of binary numbers, such that you are moving from S1, S0, S1, 2, 3, all the way maybe to S7 and back, but rather you have some states that are missed. And for instance, you say you are moving from S1, you go to S4, and then you go back to S2, and probably you go to S1, and then probably go to S0, and after you have gone to S0, you go back to S2, and probably the vice versa happens. So this kind of a counter that does not follow a sequential order in which you would want it to follow using numerical flow of numbers, that is called non-binary. And what you might find when you meet non-binary synchronous counters is that sometimes they will meet a state that is called lockout. So for instance, you are moving from states. So you are moving from 0, 1, 4, 2, back to 0 and again. So in that case of a non-binary counter, if accidentally your counter moves to a state maybe S3 that is not part of the counter flow, or S5 or S6, so to speak, then it is said to be locked out. They will never be able to transition from that lockout state to back to the normal flow. But we normally, when we are designing, we normally make a provision to move out of such states by designing in such a way that in case you find yourself in any of those possible lockout states, you always go back to your default state, which you may define it as 0, and therefore in case you find yourself out of this normal flow, which is for a non-binary counter, then your counter or your sequential system will be able to default back to the system and continue counting. So in the design of such a counter, we would always follow the same process that we have followed in designing the other counters. All we need to do is to define our state table, determine the number of flip-flops you need, then you draw your excitation table. Once you have designed your excitation table, then you just do the normal flip-flop design for the combinational logic circuit if you are not using a decoder, and end up with such a table as we can see next. So this, for instance, would be an excitation table for a non-binary counter that runs from 0, this is state S0, what we have defined in this sequential circuit is that we have 4 lockout states: 1, 3, 5, and 7. And our normal counter flow is S0, S2, S6, S2, and S4. When we are designing for such a binary counter, we would list all the possible states like we have listed here. But then we know that when we are moving from S0, we are going to S6. But if we find ourselves in the lockout state S1, we go back to the default state, which is S0. And we find ourselves in S2, we go to S4. But again, when we find in another lockout state, we go back to the default, which is S0. Again, our normal flow resumes, but we find ourselves in lockout state. Again, we go back to S0. So that is how you do the design. And if you are using a JK flip-flop, you would use the excitation table for JK flip-flop, and we would be able to have with such kind of the required inputs with a number of I don't care conditions, as we have seen with excitation table for JK flip-flop. And then you do the normal K-map design that we have made before to determine which would be the inputs that are going to JA, KA, JB, and KB. So for that circuit, would be your design, and you can see from that diagram that we are designing for, you can see that JA has been simplified to be receiving only QC bar output. Again, simplifying KA, you can see it is only receiving a 1 because there are a number of don't care conditions here that allows us to have a group of 8. Similarly, we have the inputs for JB, JC, KB, and KC. And then the final design would take the form that follows right here. You can see that after you have done the simplification, you have designed your non-binary counter that is able to mitigate the cases of lockout, and you are able to find that our combinational logic circuit, it consists only of 2 gates, one AND gate and one NAND gate, and you are able to end up with a circuit that implements your non-binary counter. So you may have another example that implements non-binary counter. I'm not necessarily going to do it. All I'm going to mention here is that you are required to do design using D flip-flop, a decoder, and an OR gate. To design a synchronous counter that plans from 2, 4, 6, 1, 7, 0, 3, and back to 5, and then repeats. So you can see this is clearly non-binary, but it is synchronous. All you need to do, the first step, is to design your state diagram, which reads state S2, go to S4, go to S6, S0, S3, S5. So these are just following sequentially through that process, and then back. So that is what we are saying. So the design would be very similar. If I list for you that the first thing is to determine the number of flip-flops required. You can see we have 8 possible states, and therefore you can say this is 2 to the power 3 is equal to 8. Therefore we need 3 flip-flops. So you have QA, QB, and QC, and then you determine what is the next state for QA, QB, and QC, and then what are the required inputs. You are using the D flip-flop, so you only need 3 flip-flops: DA, DB, and DC. You follow the same procedure, and that procedure is listed for us here. So this is what you do to develop the excitation table for our non-binary counter, and this becomes our inputs. Because we are using a decoder, we don't even need to use the K-map to design for this. We know these are minterms, and we can classify this one to be minterm 1, minterm 2, minterm 3, and minterm 4. And the one for DB are minterm 0, 1, 4, 5, and minterm 0, 1, 3, 6 for DC, and therefore you end up with this design that is quite simplified. You are able to have your 3 flip-flops right here. You have the minterms for DA are simply coming from what we have listed: 1, 3, and 4. 1, 2, 3 to 4. And then we are able to get the one that is going to DB and DC respectively, and that becomes our non-binary synchronous counter.